Now, I am going to start with the discussion of another very popular non-traditional tool for optimization and which is popularly known as particle swarm optimization, in short PSO. Now, particle swarm optimization, the concept came in the year 1995 and it was introduced by Kennedy and Everhart. Now, this is just like the genetic algorithm, is a population based approach. Now, to develop this particular algorithm, actually we try to copy something, some physical phenomena like bird flocking, fish schooling and so on. Now, let me take a very simple example. We have seen the way pigeons fly in the sky, they do not collide with each other, they use the principle of optimization. Now, that particular principle has been copied here to develop this algorithm, that is particle swarm optimization. Now, here the name indicates that this is particle swarm, that is swarm of particles, that is a population of solutions. So, we are using the term swarm in place of population and particle in place of that solution. So, in GA we used to use population of solution and in PSO it is actually the swarm of particles. Now, here these particles have memory and they try to update their position, their information, they compare with their previous situations, previous positions and try to find out what should be its action in future. So, this is actually a method where the particles can keep their memory and this memory is going to help during its search. So, we try to find out actually the P based, that is the population based, and we also find out the G based. Now, how to find out this P based and G based, we will be discussing in much more details with the help of one numerical example. But before that, let me tell you, suppose that in one swarm a few particles are there. Now, what we do is we consider their positions, initially those are selected at random and we compare their objective function values, and if it is solving the maximization problem, now corresponding to that particular set of design variables which gives the maximum value of the objective function, that will be considered as the globally best. So, I am just going to take some numerical example to make it much more clear. But before that, let me tell that we try to find out the best position, that is nothing but the P best, and we also trying to find out the globally best position, that is the PG. Now, here the ith particle in d dimensional space is denoted by capital X I, and capital X I is nothing but the collection of small x I 1 comma x I 2 up to x I d, because it is having d dimension and I varies from 1 to up to n, that is actually the n is nothing but the swarm size, and here although I have written here population size, but truly speaking it should be the swarm size in PSO. Now, P based of ith particle, now each particle, that is each solution is having d dimension. So, P I is nothing but the collection of P I 1 comma P I 2 up to P I d. Now, the globally best solution, that is denoted by P g in d dimension, that is denoted by P g 1 comma P g 2 up to P g d. Now, here actually what we do, we initially assign some velocity and position to the particle and then we try to update their velocity and position through a large number of iterations. The velocity of ith particle, once again that is denoted by capital V I, and that is a collection of small v I 1, small v I 2 up to v I d, because this is in d dimension. Then once I have got this particular the velocity updating, now I can update the position also. Now, I want to discuss like how to update this particular velocity in much more details. Now, this is actually the updating rule for the velocity. Now, this corresponds to the ith particle and its dth dimension. So, V I d represents the velocity of ith particle corresponding to the dth dimension at t plus 1th iteration. That is nothing but w multiplied by V I d t. Now, this w is nothing but the inertia weight, and we will have to assign some numerical value to this particular the w, and V I d is nothing but the velocity of ith particle corresponding to dth dimension at tth iteration. So, w V I d t plus C 1 R 1 multiplied by P I d minus x I d corresponding to the tth iteration. Now, here actually what we do is, so this C 1 is nothing but a constant that is called the cognitive constant, and this R 1 is nothing but a random number lying in the range of 0 to 1, and P I d is nothing but your that population based or the present based I should say minus x I d t. So, this is nothing but this constitutes actually the cognitive component representing the personal thinking, like how to update myself. So, this is my own thinking. So, this component is going to represent the cognitive component. Now, the last component, that is C 2 R 2 multiplied by P g d minus x I d t. So, here C 2 is nothing but the social constant, R 2 is nothing but the random number lying between 0 and 1, and P g d, P g indicates the globally based solution and corresponding to the dth iteration minus x I d t. Now, what I am going to do is, I am trying to find out what will be my x I d t plus 1. So, my aim is to determine x I d corresponding to t plus 1, and supposing that this is known, and P g d t and P I d t I have already determined, and I know the values of this W C 1 C 2 and R 1 R 2 are generated, then I can find out this V I d t plus 1. Now, here the significance of the last part of this particular expression, that is C 2 R 2 multiplied by P g d minus x I d t, it represents actually the social component. That means, if I want to improve the solution, so I will have to see what is the global best, what is happening outside, okay, and the globally based solution is going to attract that particular the solutions towards it. So, there will be some improvement. So, the social component indicates collaborating effect, it pulls the particles towards the globally based solution. So, here, so this W multiplied by V I d t, that will provide the initial momentum, and the second component is nothing but the cognitive component, and the third component is the social component. Now, let me take a very simple example, very practical example. Now, supposing that Mr. X has got some training, he has got some degree, say PhD degree, and now he has joined some profession, might be say research, he wants to improve. Now, if he wants to improve, what he will have to do is, he will have to depend on the initial momentum, there is no doubt in it. At the same time, he will have to improve himself. So, and that indicates actually the second component. And another thing he will have to do, what is happening outside the world, okay, and what others are doing, what is the globally best solution, that also you will have to keep in touch or keep track of that. Then only Mr. X or the Dr. X will be able to make significant improvement in his professional life. So, the same principle of this particular the particle swarm optimization is applicable to our life also. Now, as I told that it has got three components like initial momentum, cognitive component and social component, and using these three components. So, the velocity for the ith particle corresponding to the dth dimension will be updated, and once we are able to update this, now I will be able to find out what should be the updated information in terms of the position. So, the velocity updating is done, then position updating, that is x I d t plus 1 is nothing but x I d t plus v I d multiplied v I d t plus 1. So, using this particular expression, so we can find out what should be this particular updated position for the ith particle corresponding to the dth dimension at t plus 1th iteration. So, this particular updating of the velocity and updating of the position are to be done through a large number of iterations, and then this particular algorithm will be able to find out that particular the optimal solution. Now, this optimization algorithm, that is PSO, principle wise is very simple, much simpler compared to the genetic algorithm, and here actually there is no such complex operators like crossover, mutation and all such things. It is very straightforward, but here there is one thing has to be kept in mind, that is the memory. So, here the solutions, that is the particles, are having their own memory and they update their position, they update their velocity based on their past experience and based on actually the globally best solution. And due to this particular updating, this particular algorithm can perform both the global search as well as the local search very efficiently. Now, here all such things whatever I discussed, so I have mentioned here, W is a constant, inertia weight, cognitive constant is C1, social constant C2, R1, R2 are nothing but the random number. Now, here I just want to tell that the performance of this particular algorithm is dependent on the number of parameters. For example, say we have got the parameters like the W, then comes your this C1, then C2. The performance will depend on this particular the values of the parameters. Now, what you will have to do is you will have to find out the values of these parameters W, C1 and C2 in a very efficient way, in an adaptive way, so that this particular algorithm can become more efficient. Now, what I am going to do is, so I am just going to solve one numerical example just to explain the working principle of this particular the algorithm. But before that, let me try to concentrate on the flow chart of this particular algorithm, which I have already discussed, but let me try to summarize with the help of this particular the flow chart. So, we start with the algorithm. We initialize a population of particles at random, that means the random position and the random velocities we will have to assign, and we evaluate the fitness value by using the expression of objective function. We try to find out the fitness value for each of the particles lying in that particular the swarm. We compare each particle's fitness and with that of the current best to obtain the p best. So, we try to find out what should be the p best. Now, We compare the p based values just to find out the globally best, that is nothing but the PG. Then we update the velocity and the position, and this completes actually one iteration of this particular algorithm. Now, here we have got the checking, that is the termination criteria. If the termination criteria is met, then it is the end of the algorithm, otherwise we are going to repeat. So, once again we are going to start with the evaluation of this particular the quality of the solution in terms of the fitness, and then we try to find out p based, g based, and we update this particular velocity, position, and this process will go on and go on. So, this is the way actually this particular algorithm works, and as I told that it is very simple and much simpler than the genetic algorithm. Now, if I compare this particular PSO with the genetic algorithm, we can see that both PSO as well as genetic algorithm are population based approach. Now, in PSO there is no operator like crossover mutation. On the other hand, in GA we use crossover mutation, all such operators. In PSO actually the particles have memory, and it has got some I should say some, this is the plus point of this particular algorithm. On the other hand, in genetic algorithm solutions do not have memory, and that is why GA is suitable only for the global search. On the other hand, the PSO is suitable for both local as well as the global search. Now, the PSO carries out both the global and the local search simultaneously. On the other hand, GA is a powerful tool for global optimization, but its local search capability is poor. And PSO is faster because here there is no such operator like reproduction, crossover and mutation. It is very straightforward. On the other hand, the GA is slower compared to the PSO. Now, we have solved actually a number of optimization problems using both PSO and genetic algorithm, and based on that particular experience we can say that PSO is expected to provide better results compared to the GA in most of the optimization problem, and that is why the PSO is becoming in fact more popular nowadays even compared to the genetic algorithm. But of course, as I mentioned, there are some problems, there are some effort has to be made to find out what should be the values for the parameter, so that PSO can perform in the optimal sense. Now, to explain the working principle of this particular PSO, I am just going to take the help of one numerical example. Now, this is a very simple example involving only one variable. Now, what we do is we try to maximize y is a function of only one variable. So, f x equals to minus x square plus 5 x plus 20, and for simplicity I am just going to consider that this is a function of only one variable, subject to the condition that x is lying between minus 10 and plus 10. So, this is the range for the variable. So, what we do? We start with iteration, we set iteration t equals to 0. Let us consider that there are only 10 initial solutions for simplicity. That means, the swarm size is nothing but 10, and lying within the range of this particular the design variables, let us generate some number. For example, say x 1 0 is minus 8.0, x 2 0 is 7.5, x 3 0 6.0, x 4 0 minus 6.5, x 5 0 9.0, x 6 0 is 3.6, x 7 0 is minus 5.5, x 8 0 is minus 4.5, x 9 0 is 4.0, x 10 0 is 6.7. Now, all such numerical values for the design variables are generated at random, and within this particular the range for the variable. And for simplicity I have considered the swarm size is equal to 10. Now, based on this particular the values of the design variables, now I can find out the function value, the objective function value using this particular expression. So, if I just substitute the values for the x, so I will be getting the y values, and those y values are nothing but this. Say y 1 will come as minus 84.0, y 2 is 1.25, y 3 is 14.0, y 4 is minus 54.75, y 5 is minus 16.0, y 6 is 25.04, y 7 is minus 37.75, y 8 is minus 22.75, y 9 24.0, y 10 is 8.61. Now, remember we are solving one maximization problem. Now, if I compare the values of this particular y corresponding to this y 6, I am getting the maximum value of the objective function. So, this is the best solution, and corresponding to that actually what we do is, so this particular y 6 is the maximum, that is the best solution, and this solution is coming due to what? It is coming corresponding to this when we consider, like your, if you just see the last slide, corresponding to x 60, that is equal to 3.6. So, I am getting the best solution. That means your in this particular swarm p based 60. So, this will be the locally best. Now, if I compare actually corresponding to the location 1, the variable 1, that is p based 1 corresponding to iteration 1, that is actually we assign that is the best, because that is the starting minus 8.0. Then p based comma 20 is 7.5, p based comma 3 is 6.0, p based comma 40 is minus 6.5, p based comma 50 is 9.0, p based 60 is 3.6, p based 70 is minus 5.5, p based 80 is minus 4.5, p based 90 is 4.0, p based 10 is 6.7. Now, if you remember, initially we assign or we assume these are the values of the design variable, but this is the starting. So, what we assign is we assign these are the p based solution. Okay. Now, we compare this p based in terms of their objective function value. Now, y 6 is found to be the maximum as I told, and that is coming due to this when x is equals to 3.6. So, this particular p based 60 will be declared as the globally best. Okay. So, this is the way we will have to identify the p based as well as the g based. Now, let us assume that C 1 equals to C 2 equals to 1, that is the cognitive constant and the social constant, and W is equals to 1, and initially we set the velocities are equal to 0. So, all the velocities for the 10 the particles are set equal to 0. Now, we generally we just go for. So, we have got this particular p based, we have got the g based also, this will be the g based, we will declare that this is the g based, and so the maximum of the personal best, that is p based 60 is 3.6, and that is nothing but the globally best, that is p g based 0, 0 means corresponding to the 0th iteration, that is equals to 3.6. So, we have seen how to get the p based solution, how to get the g based solution, and we have assumed the values for C 1, C 2 and W. Now, what we do is we assign some random value, say R 1 corresponding to the 0th iteration is a 0.2, R 2 corresponding to 0th iteration is a 0.8. So, using this Now, I am in a position to find out the numerical value for this particular the updated velocity, that is V I corresponding to t plus 1th iteration is nothing but W multiplied by V I t plus C 1 R 1 t p based I t minus x I t plus C 2 R 2 t g based t minus x I t. T indicates actually your the iteration number. It is not the power, it is the superscript. Now, if I assign the numerical value, for example, say V 1 corresponding to 1. Okay. Now, the W is 0, sorry, W is not 0, W was equal to 1.0, but the initial velocity for all the particles are assumed to be equal to 0. So, this particular contribution is nothing but is equals to 0. Now, C 1 was 1, R 1 is 0.2, I am putting R 1 is 0.2, then P based I corresponding to location 1, if you remember. So, what was your P based 1 corresponding to 0? That was minus 8.0. So, minus 8.0 minus x I t, once again x I t, if we remember x 1 0 was minus 8.0. So, minus of minus, so this will become plus C 2, C 2 is nothing but 1, R 2 t is nothing but 0.8, then globally based is 3.6. So, 3.6 minus this x I t, that is your x 1 0, that was minus 8.0. So, this will become plus 8.0, and if you calculate, this will become 9.28. So, this is what? This is nothing but the velocity of particle 1 at the next iteration. Similarly, I can find out the velocity of the second particle, third particle up to the 10th particle. So, I can find out the velocity of the second particle, that is V 2 corresponding to 1, and if I follow this principle, I will be getting minus 3.12. Similarly, V 3 1 is minus 1.92, and we can find out these other velocities, and the last one, that is V 10 1 will be minus 2.48. And once you have got all the velocities for 10 particles in the swarm, now I can find out the position. So, position x I corresponding to t plus 1 is nothing but x I t plus V I t plus 1, and I can find out x 1 1 is nothing but x 1 0 plus V 1 1. So, V 1 1 I have already calculated. So, I can find out what is x 1 1, and that is equals to 1.28. Similarly, I can find out x 2 1 4.38, and all the positions I can find out, and the last is x 10 1, that is nothing but 4.22. Now, if I see the initial position, let me go back. If I see the initial position, so this was my initial position. So, this was my initial position, the starting position for all 10 particles. Now, at the end of this particular iteration, so I am able to find out what should be the position of the 10 particles at the end of this particular the iteration. This completes one iteration of this particular the algorithm, and this iteration will proceed, and through a large number of iteration, the algorithm will try to find out the optimal solution, and that could be the globally optimal solution. So, this is the way actually the particle swarm optimization can find out the optimal solution. But as I told that the performance of this particular algorithm depends on the number of parameters, and we will have to set the parameters accordingly if we want to get a very good performance of this particular the algorithm. Now, performance in the sense performance in terms of the quality of the optimal solution and in terms of the computational complexity. An ideal optimization algorithm should be able to hit the globally optimal solution in less number of iterations. And as I told, there is a chance of further improvement, and many people worked on this particular algorithm to further modify to make it more efficient and faster. Thank you.